I'm in charge of the first part of the talk related to top-down approach. So it is a work performed in collaboration with Yuri Strin from Monash University in Australia and Yeok-Shun Kim, based on Postech in Korea. So the title is Simultaneous Architecturing and Nanostructuring of Metallic Alloy by Composite by a Top-Down Approach. Internal helical shape reinforcement is widely used by living organisms in order to have a balance between stiffness and stretchability. So I take an example from Peter Fratzel, an example of the cell of food reinforced by natural helical fibers and impact on the mechanical properties. So depending on the pitch angle of the helix, he has showed that you have a strong evolution of the Young modulus, but at the same time, a large increase in the fracture strain. So, such architecture is already used with polymer. So you can find example in any shop. It is an example of a double helical reinforcement made of nylon fibers in a tube made of polymer. On the contrary, for metallic system, only external reinforcement has been implemented, so-called wrapping technique. Here you have an example of metallic tube reinforced by external double helical carbon fibers. So the question is, are we able to develop internal helical shape reinforcement for metallic alloy by a top-down approach? And to do that, we are going to revisit severe plastic deformation process. So the severe plastic deformation process is process to deform a material as much as possible, more than 1000%, for instance. And the development around this technique is impressive during the last decade. And this is the main route for producing bulk nanograin alloys now. So the principle is no change in sample geometry, plus a high pressure, like in high pressure torsion, like you have a disc here, and by axial load, you impose the pressure, and you twist as much as possible to a cumulative plastic strain. So this technique allows to have a grain size in the nanometer scale. So for iron, for instance, you can achieve a YS higher than 2 GPa, especially in the domain of the grain between 100 nanometers to 10 nanometers. So in addition, it has been shown an interest for the decrease of ductile brittle transition temperature. So it's very promising combination between YS and toughness with nanograin metals. But there is a limitation. And the limitation is in the same time that you have increase of YS, the uniform elongation decrease a lot. And it is also done to 0 for grain size lower than 1 micron. So work hardening decreases with strength very rapidly by grain size refinement, and in another sense, stretchability is almost 0 for the grain size lower than 1 micron. And this is a strong limitation because the work hardening controls the plastic flow. So we want to exploit the severe plastic deformation process to architecture the material by a top-down approach. So we have preliminary results using the high-pressure torsion. So instead to have one monolithic sample, we have used 4 quarters made of aluminum and copper in this combination. So this is a sample before the HPT, and this is a sample after the high-pressure torsion. So we obtain such a kind of sample where we have mechanically bonded copper and aluminum. And by X-ray tomography reconstruction, we see that we have started to have a spiral-like interface. But in the same time, we have not only this architecture, but we have also the grain size refinement due to the high plastic strain involved in the process. So we have a grain size of order of 100 nanometer. So in this example, I've shown that using a DSPD technique and a special geometrical arrangement at the beginning, you can have architecture at the millimeter scale, but at the same time, you can now structure each material involved in the experiment. the second series of trials have been done. We have put 6 stainless insert put in the aluminum or copper bars, and torsion has been applied to the assembly. You see here the 6 inserts along the sample, and after torsion, you see clearly that we have developed the internal helical reinforcement, but we have vein structure. It means that the materials of the insert has been pushed out during the experiment. But we have a good helical reinforcement, but development of the vein structure. So by numerical simulation, we can capture the internal architecture developed by torsion with the insert, and also we can capture also the vein structure in yellow here. So how to go further? In order to avoid vein structure, torsion extrusion seems to be the most promising process for producing internal helical shape reinforcement. So what is torsion extrusion? This is an extrusion die, but suitable to be in rotation in order to induce shear in the same time that the extrusion force. And imagine if you put an insert in the initial sample, you can create easily the internal helical reinforcement, but without the vein structure, so without the pull-out of the material consisting of the insert. So the internal helical shape in metallic alloy seems to be possible using a top-down approach. The top-down approach is based on the use of severe plastic deformation process, and so we have an opportunity for simultaneous nanostructuration and architecturation. So maybe you have seen this graph from Yves' presentation, and the approach that we have used is an approach combining nanostructure and architecture.
So the second part of the presentation will deal with another methods to get architecture materials. So I will show you, I have 50 minutes to show you that spark plasma sintering system is one of a good choice to get that kind of materials. But I will go step by step, and I will show you that actually this, we will go to smart elaboration of materials to elaboration of smart material by this technique. And I would like to thank all my co-authors which are working with me on that type of topics. So, as a general effective, so we always like to have a better cost effectiveness for producing materials, and now we are trying more and more to get not only functional materials, but also structural materials. And this is a quite good example here. This is in the United States, as you know. These guys, they are working on the bridge, which is a glass one. So you want a functional properties, which is transparency, but at the same time, you want a structural one, which is you don't want that collapse when someone work on, right? So you have different options to do that. The first one is to improve the base materials. The second one is to associate several materials, which is a composite way. Or you can use architecture materials. And I will show you that by SPS process, you can actually combine all these three at the same time. So in order to get that type of materials, we really need to investigate new elaboration route. So as Olivier already shows to you. So, and we divided by smart elaboration of materials and elaboration of smart materials. So we use in that topics always the spark plasma sintering system. So I just want to show you what it is. So it's known from the 50s. Actually, what is sintering? That's a way to get a fully dense materials. Initially, you have a powders materials. You put the powder in a mold, then you heat it up. And at the end of the day, if everything goes well, then you have a fully dense materials. But the difference with the usual sintering system is that now the heating is assured by the Joule effect. So you put a huge amount of current inside the mold or inside the powder, and then you get the fully dense. It has been shown that these sintering techniques induce lower temperature and shorter time to get the same result than the usual techniques, and also it permits to obtain refractory metals in an easy way. And I will show you some examples. Right now, there's no clear explanation about how does this thing works. There's a few hypotheses, but we are working now on that kind of things. But there's no, let's say, this is it. So we don't have this right now. Okay, so I want to show you, for example, one short example before going to smart elaboration. So my idea was, okay, if it's shorter time or lower temperature, that means that we accelerate the kinetics of the thing. So that means we can use that, for example, if you want to avoid the grain growth. So that one part of the study, I won't show you some result today, but for example, you can keep a nanostructure materials if you have a nanopowder in the beginning. Then I will show you that it's possible to obtain refractory metals and some of applications that it will open new application range, new application windows for metals that you don't think about at the first time. And then, as I said, it should enhance diffusion. So this is one of the first experiment I've done on this type of method. So we just make a diffusion couple, as Alexis said to you. So we use copper and nickel. And so we put that at 850 for 30 minutes to 10 hours. And then you measure the gradient of composition. And then you can calculate the diffusion coefficient in that case. We compare that with the HIP, high isostatic pressure, which is exactly another sintering systems, where the heating is just a classical furnace. And this is diffusion coefficient for copper and for nickel. As you can see, there's a real enhancement of the diffusion of these spaces in the case of spark plasma sintering. So that explains some of the things like lower temperature and shorter time. So can we use that now? So my first idea was, okay, if it enhances the diffusion, let's see if we can do something with that. So we took 2 copper parts, fully dense. We put that in the SPS, and then we put that at very low temperature. I will explain to you why I choose this low temperature for very short time, 5 to 20 minutes. And then afterwards, you have a massive sample, which is a cylinder, and then we machine a tensile test sample in it. Then you do the tensile test, and as you can see, this is stress strain, and you have a quite high mechanical strength, about 250 MPa, and about 25% fracture strain. If you look at fracture surface, this is really ductile, and so that means that we erase the bonding line. So even for this very short time, very low temperature, it's exactly like there is no interface anymore in that case. Just if you look at the literature, in order to get almost the same results, this guy, they put an hour at 900 degrees C. So that's, once again, this is a proof about the accelerating diffusion process in that case. So why do we choose that system? Because if you look now in the power electronic, then you have this kind of complex structure where you have a chip and then you have some insulator and copper things. And there's a big problem where, for example, when you want to put a chip on a copper in order, for example, to decrease the heat of the chip or to put connections, then you have to braze it. And as you braze it, then you introduce a new materials, and as you introduce a new materials, when it's submitted to thermal fatigue, it can break. And as you can see, the connections here, they are not connected anymore. So we said, okay, let's try if we can avoid that brazing now. So the idea was pretty simple. So you have this is a substrate which is constituted of copper plus something else, and this is a chip here. And we have another one there with the micropillar, which are doing the connection with the chip. So it's pretty easy. You put that in the SPS like that, then you put the current in, and then there's a SPS bonding. Actually, this is only one picture that I cut for the demonstration. So that means that the interface is really perfect. After 300 degrees C and 5 to 20 minutes, then you cannot remove each part. And actually, the strength here is about the highest strength that you can have in shearing for this kind of applications. So you can do low temperature bonding on a chip, which is it's possible. So there is no need anymore to have brazing in that case. So this is one of the topics we are working on now by doing that at a larger scale. Now let's move on smart materials. So we talk a lot about functionally graded since the beginning of this morning. So I want to show you one example that we've done on the SPS. So there's usually these functionally graded, they have really high potential. So we talk about a higher hardness at the surface for wear resistance, for example. They're usually not easy to obtain. I think we understood that since this morning. And so we can ask, is the SPS with the enhanced diffusion process can help that? So this is exactly what the idea that Kumpi had just before. So we take a steel powder with a composition that permits to have 100% martensite at the end of the sintering process. And we use graphite paper as a carbon source to get a carbon diffusion inside the steel powder, and so to have a gradient of carbon inside. So this is basically what happened. This is the steel, so we put graphite there, we put the current going through, and this is what you have, the hardness as a function of x. X is here, the height of your samples. This is the normal hardness for 100% martensite in that steel. So this has been done at 5 minutes for 1,000 degrees C, right? So as you can see, you have a gradient of carbon, which is about 5 millimeters in that case, which is far larger than you should have if you look at diffusion coefficient of carbon in iron. So that means that we can have this kind of really large gradient in one materials, and you can then tailor the mechanical properties according to the process parameters. Now you also see something very strange, is that here the diffusion is about, let's say 4 to 5 millimeters, but on the other side, it's about less than 1 millimeter, which is exactly the size of what you can, let's say, expect by the normal diffusion coefficient. So this maybe it's still under examination, but it seems to be the effect of the current directions. So that means here the current is going in one direction and enhance the diffusion, and in other side, it may even prevent it, actually. I won't show some results here, but you can prevent the diffusion if we want to. Let's go back to microelectronic applications now. So I already talked about this part here. There's another one here, which is quite interesting, is that these guys, they are trying to couple the copper, which is a metal, with insulating ceramics. And this ceramics is usually aluminum nitride. The big problem in that, if you do that, if your success in couple these two materials, is that the thermal coefficient expansion of these two materials are very different. So now if you have thermal cycles, then you have thermal fatigues, and then you have fracture that occur in the aluminum nitride. So this is something that these people, they don't really like it, as you can imagine. So we think about, can we replace one of the two materials in order to get exactly not that kind of problems. So if you look at the database, one materials which have the same thermal coefficient than aluminum nitride, quite the same, is molybdenum. Now you have a big problem, because molybdenum is quite good as at electrical properties, but it's really difficult to get. It's a refractory metals. But as I said in the introduction, SPS permits to get refractory metals. So this is what we've done. So we have aluminum nitride. This is a disc, actually. We put the powder, molybdenum powder on that, and we sinter that all together. So actually, we don't sinter the aluminum nitride, but we sinter the molybdenum, and we do, at the same time, the bonding between these two. So this is the parameters we use. So we try different temperature, different time to look at what is the best process parameters. So the first thing, as you can see, so you can sinter and bond at the same time. So in only one process. Now, if we look at the densification of molybdenum, we found that we can have a fully dense molybdenum, which is the only techniques that can provide densification of molybdenum in only one step. Usually you have high deformation step afterwards. So you have a very well densified molybdenum and you have a good interface. So I put perfect. I don't think it's perfect, but still it's, if you look, we did some mechanical properties, so mechanical testing, trying to shear these type of things, and this is pretty good in terms of mechanical properties. And now we are doing the same thing, but co-sintering the two of them. So we put aluminum nitride powders, molybdenum powders, and we co-sinter the two of them in order to get a diffuse interface. So we success in that, and now we are trying to make the mechanical properties of this type of things. Another type of smart materials you want to get, usually it's porous materials for different kind of application. It could be low density, you can try to find acoustic properties, or for biomaterials, for example, for hip implants, you would like to have a titanium alloys which have a low Young modulus, exactly like the one of the bone. So in that kind of, in that application, we didn't use titanium. We use another very well-known biomaterial, which is a CCM alloys. This is a cobalt-based alloys, and we sinter that for different temperature, different pressure, and we look at what happened in terms of microstructure and actually macrostructure. So that's kind of samples you can get. So each powder here, it's about 500 microns diameters, and this is a slice of a 3D reconstruction. So you see that we made this local contact. So locally we sinter the things. So that means you can have mechanical strength, but you have still a lot of porosity, and this is a distribution of the size of porosity. So this is the porosity, this is the cobalt one. And porosity, it's about 200 microns in that case, which is quite good for if you want to, for example, have some cells that going inside. Now there's another type of things you can do. So this is another type of experiments we have done. This is for micro heat exchangers. So we use now copper powder, but you want to have a very high porosity, as you can see here. The porosity is very high, it's about 60 to 70%. In that case, we mix the copper with sodium chloride. So you sinter the two of them, and then you dissolve the sodium chloride, and you can get these type of things. And now we are trying to develop that for micro heat exchanger. And last but not least, let's go back to what Olivier presents. So I won't go back on this type of application, but we will try to do exactly the same thing as Olivier done with severe plastic deformation. So the idea is, so can we produce this type of architecture with two metals, one giving, for example, mechanical strength and one giving, for example, corrosion resistance? So the idea is pretty simple. So we took a steel wire. I doubled that, so I will use my hand also. I double the steel wire, make an helicoid here, and then I put that in the mold, putting copper powder inside, and I sinter the two of them. And then I can drill a hole. I wanted a hole to make exactly the same thing as the picture, but you don't have to drill the hole if you don't want. And so this is an X-ray tomography. So you steal the steel wires going like this, and this contrast. Let's say the black one is a copper, the white one meaning no absorption. That means this is a drill hole, and so that means you have exactly this kind of structure. We look at the interface. Also, and I can say to you that we have diffusion of the copper inside the steel and the steel inside the copper. That means the strength of the interface should be okay. So that's one of the examples of funny things you can do with spark plasma sintering system. So here are the conclusions. So I hope I show you that SPS is a promising technique to elaborate smart materials. As I show you, it increased an enhanced diffusion of the metallic spaces, at least in the case considered here. We can do bonding at low temperature for a short time. You can control the process in order to get controlled porous materials, and you can also have architecture materials if you think a little bit about what you want to have. So this is still the same one, and I can say that SPS is exactly there, right? You can have architecture materials, graded materials, or hybrid materials, whatever you want. You just have to think a little bit of the way you want it. So I want to thank you for your kind attention now.